Today we have what should be a very quick topic, but it's also a very important and practical one. It has to do with solar thermal radiation. We have a figure here of the good old sun, 93 million miles away, and then the Earth itself. This is not to scale. Not that you didn't notice, right? So what we'd like to know is if the sun is emitting thermal radiation, what is the radiation per unit area that actually hits the Earth? That is, what is the irradiation on the Earth from the sun? Here's one way to answer the question. Let's consider a system consisting of the following. Here is the surface of the sun, and the surface of the sun emits thermal radiation. There's some Q dot total associated with that. If we consider that the sun is basically sitting there in empty space and there's nothing around it really exchanging energy with it, all of that Q dot has got to make it to this giant sphere that is coincident with where the edge of the atmosphere of the Earth is. So all of that Q dot here, leaving the surface of the sun, that Q dot's going to be exactly equal to that Q dot here. In other words, the system consisting of the space between these two dotted lines is a steady state system with the Q dot in is the Q dot out right there. Let us write this Q dot in on the surface of the sun in terms of the emissive power of the sun. That would be the emissive power of the sun times the area of the sun, and this Q dot over here is the thing that we'd like to know, the solar irradiation, G, the heat transfer emitted by the sun per unit area, but this time it's the area here, the area of this giant sphere that is 93 million miles away from the center of the sun. So that AL is this surface area. If we believe this Q dot, that Q dot are the same, this is how we can find GS, the quantity of interest. So solving this guy and putting in both the radius of the sun for that area and L, the 93 million miles between the sun and the Earth itself, we see that the 4 pi's cancel and we can get a very simple expression for GS, which is emissive power of sun times the ratio of these two distances squared. Okay, if we make the further assumption that the sun is a black body at T sun, we can write sigma T to the 4th ratio of these distances squared, and there is our GS. In reality, the sun is not a perfect black body, and we don't go measure the temperature of the sun and put it in here and get GS. In reality, what happens is you have planes flying around at the edge of the atmosphere measuring this GS directly, this solar radiation constant. It turns out to be a pretty standard number that doesn't change very much, and that number is 1,373 watts per meter squared. From this number, we can infer what the effective temperature of the sun is, assuming it's a black body. It's around 5,800 kelvins. So there we have it. In summary, we have almost 1.5 watts per, 1.5 meg, let me try again, 1.5 kilowatts, there we go, per square meter of energy coming from the sun here on Earth. Or do we really get that much? That's a good question. Okay, so if we did in fact get 1.373 kilowatts per square meter worth of energy directly from the sun, then it would behoove me to put all sorts of surfaces all over my house and all over my yard and just collect all of that free energy and use it for all sorts of things, right? That's a good idea anyway, right? But it turns out that that number's too big, right? That's not what actually makes it to Earth. This is what makes it to the outer edge of the atmosphere. But the atmosphere is a thing. So some of the solar radiation is absorbed by the atmosphere, right? Some of it bounces off of air molecules and bounces off of dust particles. It bounces off of clouds and gets scattered around. So the actual number for G that makes it from the sun directly to us on the surface of the Earth without hitting anything or being absorbed by anything is G sub D, which is called the direct component of radiation. It is less than that 1,300 watts per square meter. On a good day, it can be over 1,100 or even 1,200, right? On bad days, it might only be like 500 or 600. Depends on the time of year, depends on climate, all sorts of things like that. So there's G sub D. Now, one of the things that happens with that G sub S when it enters the atmosphere is some of it bounces off an air molecule here, and that in turn bounces off another one, and that in turn bounces off another one, and that in turn bounces off another one. And there are lots of rays doing this all the time simultaneously until you see that very quickly you get a bunch of scattered stuff going in all directions everywhere, right? So that's also thermal radiation, but we call it the diffuse component of the radiation. This is the part that scatters off of air molecules and dust molecules all over the Earth. So this is called diffuse because it's independent of direction, right? Diffuse radiation is what allows you to go outside on a cloudy day and still be able to see as if it were not nighttime. So if you can't see the sun at all because of the diffuse radiation, you still have thermal radiation coming at you. The number for G sub lowercase d is significantly lower than for GD, unless it's on a cloudy day in which G capital D is 0. This is usually only a couple of hundred watts per square meter. Okay, so we have thermal radiation. Unfortunately, it's not that 1300 watts per square meter, but we got some, right? Let's collect as much as we can. Here's an imaginary solar collector surface. I'm going to draw a little dotted line on there. I'm going to ask the question what the net radiation heat flux going into the surface is due to this thermal source. Okay, so let's start with G capital D. So G capital D hits the surface, and I can collect all of that. No, well, there's something wrong with that. One, I forgot G lowercase d, but there's something else wrong with this. Notice where the sun is, okay? If the sun were over here, wouldn't that be better? If the sun were over here, that'd be a lot worse, right? Because the direct stuff coming from the sun doesn't see that surface. So I have to modify that G capital D by multiplying it by the cosine of theta, the zenith angle, or the normal to the surface that the surface makes with the sun itself. Actually, I shouldn't call that the zenith angle because the zenith angle is only measured with relative to the Earth itself. This is the normal to the surface at hand. That's theta. So let's take GD and multiply it by cosine theta. And we'll add G lowercase d, no cosine theta needed, it's diffuse. So that's what I collect when I put a surface out on outside to collect thermal radiation. Well, let's not assume that all of that's absorbed. This might not be a black surface. So multiply that guy by the absorptivity, and now I've got it. No, still not quite, right? So this is coming from the sun, and I've completely ignored this thing called the sky, right? So in this picture, I've drawn an imaginary dome, an imaginary surface that completely surrounds the Earth, and I've called it the sky in quotation marks. You know, the sky is not really a single surface all at one temperature, it's the entire atmosphere. But for thermal radiation calculations, this is a handy model that does a pretty good job. So this pretend surface that I'm calling the sky is going to have a temperature called T sky. This is called the effective sky temperature. What do you remember about really, really, really big isothermal surfaces and how we can model them? As black bodies, right? So we can model T sky as being a black body, and we get some radiation from that too. So let's add sigma T sky to the fourth, and there is the radiation that the sky is emitting and hitting our surface with. But wait a second, we don't want to assume our surface is a black body. Multiply that by the absorptivity as well. Now I'm done. Still not done. I got another modification to make. We're after the net amount of thermal radiation due to solar sources entering this surface. The surface itself, because of its non-zero temperature, is emitting radiation back to the surroundings, right? So let's subtract that radiation from our expression. Sigma T surface to the fourth, subtract that. Again, I don't want to assume that the surface is a black body, so we'll multiply that by epsilon. And now, finally, I'm finished. No, still not done. There is a major, major theoretical mistake that I've made in this equation. I can fix it with a stroke of a pen, or I guess the stroke of a virtual pen in this case. And it has to do with this alpha and this alpha. This alpha is what fraction of radiation coming from the sun is absorbed by the surface. The sun at 5,800 kelvins. It is behaving significantly different than everything else this surface could ever make contact with. You and I walking by, the box that we put it in, whatever. The temperature of the sun being thousands of degrees different than this means that the radiative properties of the surface for those wavelengths of the sun could be significantly different than its radiative properties for energy coming from everything else. And in fact, that's usually true. So for thermal applications, I almost always define one absorptivity specifically for sources of radiation being the sun, and I call that the solar absorptivity, alpha sub S. And I do not want to assume that that alpha and that alpha are the same. All right. Now, having said that, there is some good news because this alpha and that epsilon, what can you say about those? You can probably say those are very close to being the same because of Kirchhoff's law. The sky temperature and the surface temperature, those are probably pretty close to each other, and the whole alpha is equal to epsilon thing works, right? This epsilon is not equal to that alpha, but it's probably equal to that alpha. So I can make a minor simplification of this and get rid of alpha and just write this as epsilon and combine those two terms. So when all is said and done, here's my net radiation flux that I get when I expose a surface to solar radiation. Absorptivity of the sun, or I should say absorptivity for solar radiation, times the total irradiation from the sun, plus epsilon sigma t sky to the fourth minus t surface to the fourth. There we go. So in the end, when you have solar applications and you want to know what the net radiation flux is for thermal sources, you can use this good handy plug and chug formula, and life is good.